we're going to take a pretty childlike view on rendering, really. In computer graphics, in the summer term 2025, at the Bocholt campus of Westphalian University of Applied Sciences. Good day. Computer graphics again. We start with ray tracing this time. Pretty much a topic maybe for computer graphics too, because you can teach it as an advanced topic, but I would like to take the introduction seriously. Just a second. Doesn't go as I expected. No, not this way. This way. Ask your 5-year-old self, how does vision work? Take your 4-year-old or 6-year-old self, but not much more and not much less. How do you think that you thought vision worked? Yep. Take the cube mic, throw it around, and let's see. No, we're talking. Yes, a 5-year-old would not be talking about the field of vision. Yeah, but yeah, okay, just go ahead. Yeah, you see things more below than an adult, but what, as a 5-year-old, what is below? What is an adult? What do those people that are so tall even see from up there? How can they reach toys? Yeah, 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 absolutely. Didn't want to make fun of you, just fun of the situation, talking about 5-year-old vision understanding, but that is what we're going to do in ray tracing. So just go ahead. So there needs to be light shining on something, and you would have thought about light shining onto something. Right, interesting. This didn't go to plan, but anyway. Um, no, this is just the wrong window. Let's get back to this picture from 1525 that might be already explaining ray tracing. How does what is ray tracing? Let's again look at this picture and keep in mind that we're still talking about your 5-year-old self. And then we will be talking about a more adult view on this picture. Okay, maybe this one. Oh, okay, I need to go back to this question. Did no one consider vision rays? Something is emanating from your eye, and if it hits something, you see it? No? Okay, then it's just crazy me. But keep that idea in mind. Your eyes are emitting stuff. If it hits something, you see what is hit. Now coming back to this picture. What is ray tracing? How does this relate to this picture? Yeah, pass the mic, please. It will be from one single point of view. So whatever this guy is painting, it will be from one single point of view because he has this fancy eyepiece where he can place his eye and look through this glass thingy and then just paint dots or paint shapes that he is seeing. Where is the vision ray here? By the way, this is also from the same book from 1525, and this image is also explaining ray tracing very well. What are those two people doing? Exactly. We again have no, let me take this one. We have again this fixed point of view with a thread, call it the vision ray, going to this stick that the other guy is holding and pointing at a point on the object. And this person is holding a pen at the very position where the thread is crossing the frame. Then they're probably releasing the thread, closing the lid, and the guy is making a point or a mark on this lid. And then they repeat. So here you have someone, call it sampling this object, placing sample points on this object. This is a lute, a musical instrument. And the other one is marking the 2D location or the 2D projection of this sample on the canvas or on the lid or frame or whatever you want to call this, right? This is a bit different. We're still seeing sample points of this guy being painted here, but this person is rather scanning the image and marking every point on the image with the color that he's seeing. And again, this time on the just a second, on the invisible vision ray from here through there to the object. Are vision rays a thing? Do they exist? Do our eyes emit rays that hit objects, and if those rays hit objects, we're seeing them? Yes. Um, there are light sources in the world around us. So it's just the opposite way around. There are light sources in the world around us, emitting light, illuminating the objects around us. The objects are reflecting the light, and a tiny fraction of this light is going to make it into our eyes for us to see the world. So pretty much what you said, if there is light, you see stuff around you. Do vision rays work? Yes, you're right. They absolutely do work because we have geometric optics, and this works both ways around. You can do the computations from the light source to the object to the eye, or do the inverse from the eye to the object to the light source. It's the exact light path, just inverted. So, again, to your 5-year-old self, maybe you don't remember the vision rays, but you can use them here for ray tracing. And we will see how. All right, we had this with this. And just from those pictures from 1525 and the idea of vision rays existing, we can describe ray tracing, most parts of it, or the fundamentals of it. And especially for the first image that I showed you, where the painter is sampling the image. Not so much for the second image, where the assistant is sampling the object. You could even do it that way, but it's easier to describe in the way to sample the image. So for each pixel, you're sampling the image. You send a ray from the eye to the scene, and this is what was happening in both images. One, in the first image, was standing at this eyepiece and looking through the screen into the scene, drawing what he was seeing. With send the ray from the eye into the scene, that could better be seen on the second picture. We see the actual ray, the thread that they were moving around in the scene, through the frame, through the image, to the object, and then just fill the pixel that you're sampling with the color that you're seeing. There's just 2 for loops, and you're done. A third one. 3 for loops. Who does already see the 3 for loops? How many for loops do I need for the line for each pixel in a 2D image? Yes, yes. An image is a 2-dimensional thing, and you go in one direction and also into the other direction. And first you cross one, then you make a step in the next direction, you cross it again, and so on and so forth. 2 for loops. Where is the third? I wouldn't use a for loop either for that. But you're correct, the ray is hitting an object, being reflected towards another object, towards another object, towards another object, hitting the light source. That is either a while loop or just recursion. But you need a third for loop. By the way, you wouldn't want to do it that way. Let's talk about this later, and that is the reason why you use vision rays and not light rays in ray tracing. But let's first find the third for loop. Because there needs to be a third for loop, just for the reason that scenes that don't require this third for loop are pretty boring. So 2 for loops to determine the pixel coordinate, right? And the third for loop, do I see this workstation, do I see that workstation, the monitor, the table, the ceiling, the tree, one of the leaves, the other leaf, the next leaf, the next leaf, the next leaf, the sky, and so on. So for each x, for each y, for each object in the scene, down to for each triangle in the scene. That are the 3 for loops, basically. And the third for loop can be split across the groups in the scene, for each group, then the sub-objects, and so on and so forth. So basically a bunch of third for loops, depending on your scene. Why do you want to use vision rays emanating from the eye and not from the light source? Yes, absolutely. You want to trace those rays that are hitting the eye. Just think of it the other way around. How many photons is the sun emitting every now and then? Let's make it 5, just for simplicity. There are more, but let's just take 5. How many of those 5 photons emitted from the sun will hit your eye? And if the sun is emitting just 5 photons, there is an exact number as an answer to this. A pretty exact number because there are so many leading zeros. Okay, if the sun would emit just 5 photons, none of this is likely to hit your eye because your eye is pretty small compared to the sun. And your eye is just in one direction seen from the sun. So you needed to trace many rays from the light source through the scene, reflecting off the objects in the scene towards other objects, being reflected off those objects again and again and again to finally not hit the camera. So why trace these rays in the first place? It's more performant to do the other way around. Absolutely correct. Trace the rays that go through your image into the scene and collect the color that you're seeing there. To do it photorealistically, you need more rays. You need to trace them further. So those rays emitted from your eye onto the objects in the scene need to be reflected off the objects. Again, invert this. The light goes to the objects and is reflected towards your eye, but you trace it the opposite way. And if you then want to do global illumination, you need some rays being emitted from the light source into the scene. Let them reflect off the objects and then combine both, but don't trace the full path. This wouldn't work both ways. You wouldn't hit the light source if you were tracing the ray from the eye through the image onto the object, being reflected off to another object, being reflected off to another object, and so on and so forth. You wouldn't hit the light source. If you start from the light source, same problem with your eye. So we need to find some simplifications that bring both together. And for emitting rays from the eyes into the scene, it's pretty simple to reach the light sources. So there is a simple simplification to have light in the scene. It is still pretty simple to do a bit more. We'll see that later. But if you want to have global illumination, so a red wall reflecting red light onto the floor, for example, or onto a white wall, you need to first trace some light from the light source to the red wall to the white wall, store it there, and then go from the eye to the white wall and gather the red light that the white wall received. But you won't trace the red light immediately to the eye because you just wouldn't hit it. Okay, but basically a ray tracer is just 3 for loops drawing the pixels. Okay? Who did this first? Well, apparently there is some sort of description from 1525 you saw the images, and if we're done with ray tracing, you probably see ray tracing in those images. But something that you could call ray casting, this is just trace a single ray and be done with it, was published in 1968 by Arthur Appel in a completely, not completely computer graphics unrelated topic, but rather in engineering. And Arthur Appel solved something like hidden surface removal with ray casting. Consider this being a digital engineering drawing of some sort of console. So construction drawing, if you will. And you want to print it onto a piece of paper in such a way that you can see which of the sides is outside and which of the sides is inside the object, or which edges are on the outside, which edges are on the inside. Because it looks better or more realistic if you draw the hidden edges with dashed lines. But for this to work, you need to determine that they are hidden edges, right? So you think about the perspective that you want to see the object in, trace rays from the eye, and see which surfaces are hit first. They need to be the front-facing surfaces, and all the others are the back-facing surfaces that are hidden behind them. And so you can decide which one is front, which one is back. If you can do this from the eye, you can go even a bit more realistic and do the same from the light source to determine where is light and where is shadow. And how are in what angle are the surfaces or the individual faces of the object facing the light source to determine how bright to paint them. So you take each light source, trace rays into the object or into the scene, hitting the object, and just noting at the intersection points, there is light. And there is light again. There is no light. There is no light. There is no light. There is light again. And then you're just counting either the crosses, there is light, or you're counting the crosses, there is no light, and decide to draw shadow or light. To determine that, you have a light source probably shining into this opening, so that you have a bright spot here. Let me do it for the stream. You have a bright spot here, so there needs to be some light source shining into the object. But there is another light source that is casting this shadow. But it's only a medium shadow, because there is a darker shadow over here, because both light sources are blocked there. And you can determine it by tracing vision rays from the light sources, and just the first rays. And if you have this, you can go all fancy and render shaded architectural drawings of buildings. Probably expensive buildings, if you take this drawing. 1968. Not for the sake of doing computer graphics, but for solving engineering problems. For drawing engineering drawings to paper. Well, then pretty much computer graphics took off, did rasterization, and could apply similar principles, lighting and shading, and yeah, we could do surfaces, spheres, triangles, objects, and all that stuff. But the computer graphics community did it in a different way. They used rasterization for this purpose. We'll deal with rasterization at the end of the term. But why did they do it? It was computationally simpler. It was the less expensive way to compute this. Ray tracing requires much more computing power to do it properly. But currently we are having this compute power available. And again, this is the 5-year-old impression of how you see stuff. There needs to be something that your eye is doing to the scene, because you perceive the scene through your eye. ray tracing made it into computer graphics in, when was it, 1918, when Turner Whitted rendered an image of two spheres above a plane. Well, nothing special to it, right? Two spheres shaded above a plane. Well, special if you consider that one sphere was reflecting the light and the other was transparent and did also consider refraction. And this is hard to achieve with rasterization. And so this image, there's also a color version available if you look it up on the internet. This image was pretty revolutionary. And it still works on the same principle that you are tracing a ray from the back to the beginning. You start from the eye into the scene. You hit an object. You can draw it. If the object is transparent, you can trace another ray going through the object, and you see what is behind the object. If the object is reflective, you can bounce that ray off the object in the direction of the reflection and see what is being reflected by tracing another ray. And then tracing another ray if you have more reflective surfaces, or if you don't have reflection or don't have transmission, you just do the Arthur Appel way, go from the light sources and see if there is shadow. And you have everything in here. You have the opaque surface with a checkerboard that just receives light and shadows of the spheres. One shadow of this sphere, the other of this sphere, plus the shadow of a transparent sphere. Because this shadow is brighter than this shadow. And there's just one light source, hopefully. Then you can see through this sphere, so you are able to trace rays through transparent objects. There is even refraction at work because you see this distortion. The sphere is being lit from the outside because you have this highlight, so you see the reflection of the light source. And you see the reflection of the scene on this reflective sphere, plus you see the reflection of the light source as this tiny bright spot on the metal sphere. Right? And again, it's vision rays. So, ray tracing. How does it work? Apparently you need spheres. Turner Whitted showed us. And it's a simple thing to do, to just do spheres at the beginning. And you need an eye, or a camera, or a virtual eye, or whatever. And you better have light sources, because you need light in order to see stuff. And to later properly shade stuff to see surfaces properly. In this setting, you want to generate an image, so you need the image plane. Remember the drawings from 1525? You need an image plane where you draw the stuff you are seeing onto. So you have the image plane. And then you trace a ray from the eye through the pixel for which you want to determine the color into the scene. And if you're lucky, you're hitting an object. And if you have light sources, you can determine if there is light or shadow. And then just draw the color into the pixel. Right? Okay, you need a bit of math. But hopefully, just the math that you learned in school. Not much more. So, what do we need? We need rays, apparently, because it's ray tracing. And what is a ray? If you look at this formula, does this look somehow familiar? Let's start with the left part of the left side of the comma. What is this? And just maybe stop a bit to make the notation clear. Upright, bold, lowercase letters denote vectors. and slanted or italic, lowercase, non-bold letters denote scalars. So just plain old numbers. But I don't want to draw the arrow on top of the vector symbols, because this is the English notation, and most of computer graphics literature is in English, so let's use it here. Maybe, but it depends on the notation. Maybe I use the vector arrows on the blackboard because I'm terribly bad at drawing bold-faced letters. Anyway, so boldface, lowercase vectors, lowercase slanted numbers. What is the left side of the comma? What does this tell you? Where did you see this equation? And hopefully in school. Yes, this is a linear combination of two vectors. That is correct, but let's call it just a line. Yeah, there's a line equation. And now take the right side of the comma and merge both. What do you have? Well, apparently array, but what does that mean? And not both sides, just the t is greater than 0. What does this mean? Because this part is just helpful. Second, the t is the distance from the eye to the object, but okay, you started it. Only if the length of d is 1, then t is the distance. Otherwise, t would be the distance in terms of the length of d, but that is just for convenience. If the length of d is 1, then t is the distance. Yeah, so you have to normalize d. But why does t need to be greater than 0? Yeah, but if we're just talking distances, I could refer to objects behind of me and talk about negative distances. Why don't I need negative distances? I can't see is correct, but not I can't see the things after or behind the things that I see. It's just this way. Now I can't see you anymore. Why wasn't I able to see you? You were behind me. You were at negative t from my eyes. If d is pointing this way, as vision rays would. Right, so a ray is closely related to a line, but call it maybe half line. It has a starting point. A line does not have a starting nor an ending point, but a ray has a starting point, and that is P0. You start at P0 and go into the direction of the ray, and T just denotes how long you're traveling. Okay, so we have points on the ray that I can compute starting at the origin, going distance steps along the ray, distance meaning a number of steps along the ray, in the direction of the ray. And since this is a ray and just considering 1/2 of the line, I need t to be greater than 0. I could also say t greater or equal to 0, but I don't want to see objects that are exactly inside my eye. That would, despite of terribly hurting, it might cause some problems if t would be allowed to be 0. And then again, for t to denote the absolute distance, I need to normalize d in order to have d with a length of 1. And this double bar is just a fancy or short notation for the absolute value, or in German, the Betrag of the vector. So this has to be 1. And then I get all of those points starting here. Well, now t has to be greater than 0, so excluding p0, all the points on this arrow and on this dashed line going on forever. That is array. And if you were to implement this, you need a data type for arrays. If you were to implement arrays, you need a data type for vectors, for 3D vectors. And again, just for the notation, we are using column vectors. But since they are taking so much space, I transpose them in the notation and transpose them again to make column vectors. This is just a notation for saving space. And again, it's the English notation, so it's brackets and not parentheses. But it's just the same as you would have done in school. Right, first the dx, then the dy, then the dz on top of each other, do parens around them. It's just a different form of writing them. So we have the arrays, we can trace them through the scene, hit objects, determine their color, and yeah, we need to store colors. We already had colors like 2 weeks ago. We said RGB, red, green, blue, would be enough components for the beginning. Well, you can even store spectra here and compute them, but typically you have RGB images at your computer to look at. The notation is slightly different. Maybe I made this notation up, but if you think a bit more about this, you have like 3 numbers combined into 1. And if you want to compute with colors, you have 3 completely separate rows that you're writing. So just like if you were to notate different cases in a math equation, you also take those curly braces to say case 1, case 2, case 3, and then you combine all those 3 cases and continue your equation that you needed to split into several cases. And that is what I want to denote with the curly braces. There are just 3 separate numbers that are combined, and they work completely independently and differently than vectors. The addition is the same. If you add 2 vectors, you add the x components, add the y components, and add the z components to make up the x, the y, or the z component respectively. It's the same for colors. You add the red channel, the blue channels, the green channels, and have the resulting color. But you can multiply colors in a very straightforward manner. You multiply the reds to get the resulting red. You multiply the blues to get the resulting blue, and you multiply the greens to get the resulting green individually. But if you were to multiply vectors, you have 2 ways to do that. Which ones? And there is a different meaning to multiplying vectors than to just multiplying 3 numbers 1 by 1 or component by component. What are the 2 products for vectors? And again, this should have been just school math. Maybe the advanced math course, maybe it depended on the school, but it's not fancy math that we're doing here. And then again, we can interpret vectors as just a fancy way of writing more equations into a single line, pretty much doing 3 times the same stuff. What are the 2 products? Just right, yes, dot product and cross product. let's not look at them right now. Okay, that is the data types you need. You need the vectors in order to form the ray, and you need colors for the ray to collect the colors out of the scene into your eye or into the image. Maybe you take also points into consideration that carry a meaning. And maybe also normals. What could that be? What could the difference be between those three? That are all three-dimensional vectors in mathematical terms. They're three-dimensional vectors. But there is a difference because of their meaning. Careful. Normals are not normalized vectors. Even worse, normals don't necessarily need to be normalized. They better be normalized, but they are not per se normalized vectors. Yes, that is the important part. Normals are the vectors that are orthogonal to the surface they belong to. They define the orientation of the surface as defined by the normal. We just have the line or the ray equation on this slide. In a way, the parametric line equation. There is also another form of line equation where you can see the normal on the line, or maybe you remember the plane equation that used the normal. And the normal is the vector that is orthogonal to the surface that it belongs to. It does not need to be normalized, but it is advantageous if you normalize it because computations get simpler. That is the normal. What is a point? Yes. If you want to do it correctly, a point is closely related to a vector that starts at the origin. But then again, you clash with a vector definition because vectors are everywhere. But anyway, a point is a special type of vector that is fixed, whose beginning is fixed to the origin of the coordinate system. So the end is denoting a 3D position. A position in space, a 3D position in space. That is denoted by a point. And what is a vector? And why is it called D in this slide? Vectors are used to describe directions. Points are used to describe 3D locations in space. There can be a direction, so a vector, taking you from one point to another point. The surface normal is the direction orthogonal to the surface that it refers to or that it belongs to. It is a vector, apparently. Apparently, it's a direction plus it has the state of being orthogonal to the surface. So there is different meaning to all of those. What does this mean mathematically? You can add vectors together to get another direction or an overall direction, no problem. You can take the difference of 2 points to get the direction taking you from one to the other. You can add a vector to a point taking you from one to the other. Why would you ever want to add points? What should that be? One location in space, another location in space, and what is the sum of those two? I don't think there is any useful meaning of the sum of 2 points. There is a useful meaning of the sum of 2 vectors. That is another vector. So if you have, consider you have 3 points. Just let's make it this way. Blank. Interesting. We have a P0 and a P1. Then we can create the vector D1 taking you from P0 to P1. And D1 is just P1 minus P0. That is all vectors, so I leave any arrows or boldface out. Okay? We can take a third point, P2, and a second direction, D2, with D2 being P2 minus P1. Okay? And then I can think of a D3 as D1 plus D2, which is P1 minus P0 plus P2 minus P1, which is the same as P2 minus P0, apparently, because I drew the arrow from P0 to P2. So that is why you need to be able to add vectors in order to take you from one point to the other, to the next, to the next, to the next, and so on, to get the immediate or direct way. But why would you ever want to add 2 points? What would this be geometrically? The sum of 2 points? No idea. The normal, once again, I have a surface with a vector pointing out of it at a 90-degree angle, and I would want to denote this as n normal. A special vector being orthogonal to the surface. And whatever I do to this normal, it has to stay orthogonal to the surface. And so maybe I need some sort of different math that applies to this vector than I would have to apply to vectors in general, or directions. And we will see this difference when we're talking about transformations. So it might be important to have a different data type for this. Because if you have a language, a programming language that is capable of dealing different or dealing with those individual types differently, you could still say, or still write P1 minus P2, D1 minus D2, N1 minus N2, and have the right or the correct computation being performed. So it's convenient to have, different types for those different guys. Okay. Well, and if we can do vectors, we are actually doing 3x1 matrices, and then we can do 4x4 matrices as well. But we need them. We need them when we're doing transformations. And who of you has seen matrices in school? School math. Nothing more. You don't need fancy math from the university. Maybe you heard about matrices and vectors, so linear algebra, at the university in the math, the fundamentals of mathematics courses that we are offering. But some of you, and that was depending on the course you took, depending on the school you went to, you learn how to compute with matrices and vectors early in your life. And there is not much of the mathematics or of the computations that we need here. But we come to them later. That is the data types that you need to implement if you want to do it comfortably. If you want to go the hard way, this is just floating point numbers. Well, 16 floating point numbers, you can deal with them. Just give them a different name and go with it. But it's not convenient to write. Okay, how to generate rays? No, the question's up to here. Right. How to generate rays? Well, take the eye, take the image plane, shoot a ray. So you need the eye, and you need the image plane. Shoot a ray through a pixel. Done. Well, yeah, shoot the ray. Piece of cake, right? Not quite. What do you know about the image plane? Because we need to be a bit careful if we want to do this properly. But again, there is not much to it. It produces fancy images, but the algorithm behind it is pretty simple. What do you know about this image plane? Well, it tells a bit too much at the moment. But anyway, yeah, just what do you know? Correct. So correct answer, or many correct answers. But as I said, the image is telling too much. It shouldn't tell everything right now. Should have deleted some of the lines. But you said you know the position of the image plane, and you know more. You know the width, the height, and the focal length. Hopefully. And you were talking about pixels. We're still talking about world units because we are just in eye space, or call it camera space. You just opened your camera and looked at the image plane. And the image plane that you're seeing inside the camera, without looking too closely, you're just seeing a width, a height, and a focal length, and are able to measure them with a ruler, a tape measure, whatever. And this is in world units. So centimeters, meters, millimeters, you name it. And you find them here. This is the width of the image plane. That is the height of the image plane. I should do it with a red dot. This is the width of the image plane. That is the height of the image plane. And that is the focal length of the image plane, or of the camera. Brennweite in German. The focal length tells you the distance between the eye and the image plane. And that is the eyepiece in the first image that I showed you on the screen that the person was drawing on, or the hook in the wall, or the distance from the hook in the wall to the frame with this lid that could be opened and closed. That is the focal length. And you can measure it in, again, centimeters, millimeters, whatever. The same applies to the width and the height. And there is a simplification hidden that we should take. How do the position of the eye and the image plane relate to each other? That is not very good to see in this image. Not that good, a bit. Maybe take a look at the dotted line here, at this dotted line. The eye is located straight above the center of the image, orthogonally, if you want to simplify it. There are applications where you need to move the eye out of the center. We don't have to have it placed at the center, looking orthogonally or straight through the image plane. But for the sake of simplicity, just use this central projection, where the eye is looking at the dead center of the image plane. Because this helps you to determine the camera coordinate system with just 3 vectors: a side vector, an up vector, and a gaze vector. But the gaze vector. The vector of the direction that you're looking in with the overall system. So where do you aim the camera? In which direction do you aim your camera? Okay. And those are these 3 vectors. The side vector is pointing to the right of the image in the image plane. The up vector is pointing to the top of the image in the image plane. Both vectors are coplanar to the image plane, so in the image plane. And then there is one vector orthogonal to both, and that is the gaze direction, just the direction that you aim your camera in. That is not, maybe that is the viewing direction, but then we have a collision with this D of the ray, that is the viewing direction of the individual ray, so let's call it the gaze direction of the camera. Okay? We need to compute those directions later. But we'll do. And now we're taking the 2D image. Not the image plane in the camera, but the image represented in our computer. And if we're looking from the eye in the camera through this pixel, it would be this pixel in the image. Right? Okay. What do we know about the image in the computer? Not the image plane in the camera, but the image in the computer. You already mentioned it. There is a number of pixels horizontally and vertically. So in this case, 3 pixels vertically, 4 pixels horizontally. And we are talking about the pixel 2, 1 that we are looking through and for which we want to determine the color. Right? Does the number 2, 1 suffice? Is this correct? Is this the correct number that we need to use? That is pixel 2, 1. If we take the 2-dimensional array of colors that we talked about last time, this would be index 2, 1, or just the opposite way around. The first index would be 1, and the second index would be 2, because arrays, at least in C, are row major. Do we work with 2, 1? Well, in the for loops, yes, but do we use 2, 1 for the ray generation? Are we looking straight through position 2, 1 in this coordinate system? Where is position 2, 1? Position 2, 1 would be here. But we're looking through this position. Careful. If we want to look through the pixel's center, let's assume we want to look through the pixel center, then it's not position 2, 1 that we're looking through, but which position are we looking through? Which position do we need to take? And this is German notation on the next slide anyway. 2.5, 1.5. We want to look through the center of the pixel. So we're not talking integer pixels anymore. And that is why I use the word sample here. We can sample the pixel. And with just another for loop, the fourth one, we can do oversampling. We don't just need to look through the center of the pixel. We could also look through 4 additional samples in the pixel. Or take more, let's take 8 around here. Or do a normal distribution of samples centered here. And sample many more samples around this pixel. Then we would do oversampling, anti-aliasing, and smoothing of the image, getting rid of artifacts. With just a 4th for loop. Just taking different samples. And not changing the algorithm in any way. Just introduce another for loop and you get oversampling. Well, you need to take the average, but anyway. It's just another multiplication at the end. So careful, if we want to paint pixel 2, 1, we need to sample position, pixel position 2.5, 1.5, in order to generate the ray through the center of this pixel, generate the ray to the position on the image plane that is equivalent to the pixel in the 2D array of colors represented in the computer. And then we have a camera. Well, if we have another data type, just to make it a bit more type safe, we need 2D vectors and interpret them as pixel position or sample positions. You could even say I have pixel positions. There are 2D integer vectors. And from those 2D integer vectors, I can generate samples, 2D floating point vectors. Maybe that is a bit too fancy, but that is for you to decide if you are writing a ray tracer. You can make up any type you want to be as expressive as you like and to tell the things apart that are different, if you like. But anyway, you could even address pixels with 2D floating point vectors. It wouldn't matter. At least if you say you want to go through the center of the pixel. Why is the center of the pixel a good idea, and why not so much the upper left corner? Don't you see? You're seeing this one. So the upper left corner. What is the problem with the upper left corner if you want to paint this square? So talking about the other pixels, I have a counterexample for it, but you're right in saying that the upper left corner of the square is a pretty bad representative of the whole square that lives completely right and below your sample. So better take a sample that represents the pixel better. So any object in here is more likely to be hit by this sample or a ray through this sample than a ray through this one. If you were to do oversampling, coming back to the other, to the shooting rays through other pixels, you wouldn't just place your samples inside this pixel. You would most likely take a normal distribution centered around here, extending into the next pixels. So looking slightly left and slightly right. You probably would want to do that and generate samples outside the pixels, but not so much. But you would like to take those into consideration as well to get a better representation of this pixel. Because again, objects located here would have an impact on this pixel. And if you were to distribute samples through the image plane, maybe you miss this one, but you would hit the same object if you sample here. So careful. And you also want to take, if you want to do anti-aliasing, you wouldn't want to introduce a grid-like structure in the samples if you want to draw on a grid-like structure, because otherwise you see artifacts. You need to sample differently in order to not see artifacts. Yeah. All right. How to bring both together? We have the image in the computer as a 2D array of colors with integer indices going from, in this example, 0 to 4 and 0 to 3, floating point samples through the pixel centers, with an image plane in the camera, let's say 3.2 centimeters wide and 1.8 centimeters high. Well, whatever that format would be. How to relate those 3.2 centimeters of width to the 4 pixels in this direction? Well, terribly bad example. 3.2 divided by 4 is 0.8. Let's take 1.7 or square root of 17. Well, let's do this in inches, because that is a maybe American camera, North American camera. How do you bring both together? Because the for loop tells you 2, 1. Adding 0.5 brings you to 2.5, and that is what you can do in the computer, but we need to trace the ray here. But you're in the for loop with 2.5, 1.5. I'm always taking the different cup. The wrong cup. T's in here. Tea used to be in the other cup in this morning, but now it's this one. What's the connection? It's just some division, multiplication, and addition, if you like. Yeah, maybe. Remapping. Take an intermediate coordinate system that is the same in both. And it's pretty convenient to say that is a coordinate system ranging from -1 to +1. Because then it's pretty easy to do the division and the multiplication. If you're ranging from -1 to +1 here, and again, let's take this 3.2 centimeters on the width, with the eye sitting over the dead center. So we're talking about -1.6 to -1.6 here to +1.6. That's just a multiplication. Multiply with 1.6. And I think it was 0.9 in the other direction. If you have a way to say this is -1, this is +1. How do you need to do this? How do you get... How wide is this in pixels? Yeah, 4. Apparently. How wide is this in this intermediate orange-brownish coordinate system? Yeah, 2 of whatever unit. So you have a width of 4 and need to bring it down to a width of 2. How do you do it? You divide it by 4 to bring it down to a width of 1, because at that point you don't care about this orange-brownish stuff. You're down at 1. Then you start to consider the orange-brownish stuff and need to scale it up to the width of 2, so multiply it by 2. Because it could also be as well 17, and then you'd be better off to just divide by 17. So where do you divide by the width that you're starting from, bring it down to 1, scale it up all the way to the width of 2, multiplied by 2. With one problem, You're still starting at 0, and you're reaching 2 over here. What to do to bring it from -1 to +1? If you have the range, where's the camera? Here it is. What's the direction? 0 to 2. Just move it a bit, and then it's -1 to 1. Just shift it by 1. Done. That's all there. So divide it through the pixel width or height, multiply it by 2, shift it by 1. And then you have the pixel or sample coordinate in this canonical coordinate system from -1 to +1. Then you need to consider width and height over here, and just scale this coordinate system up again. And then you have the measurements over here. Okay? We still need side, up, and gaze. Maybe later. Let's say we have them. If you have them, you can do the computations, right? How? How would you want to do that? You know, this is pixel or sample 2.5, 1.5. Well, yeah, divide 2.5 by 4, multiply it by 2, shift it by 1. You have the position here. Take the position here in this orange-brownish coordinate system. Scale the position up by the half of the width, because this is symmetrical. There's -1 to +1 and not 0 to 1. So scale it up by the half of the width, and you are here in world units. Or at least you know how far you need to travel to the side in world units. And take this as a factor to the vector of s, if s has the length of 1. Then you can use the factor as the distance you need to travel along this vector, and yeah, you know the pixel position in 3D. And again, this is just multiplication, division, plus, what is it? Division, multiplication, minus multiplication. Multiplication with a vector, but there's just 3 multiplications anyway. Okay. Then you're here. Then you have a position in 3D camera space that you can take, subtract P0, and you get the direction. Well, you need to normalize the direction, but that is a math problem. Okay, so you can compute directions. We do the math at the end. All right, we can shoot the ray through the image, into the scene, and hit the sphere. How? How would we want to do that? The good thing is, you can pretty much look up the result in a math formula book, if you approach it the right way. And although this is computer graphics in the, 4th semester of your undergraduate course, it is pretty straightforward what you're doing here. What is a ray? What is a ray? Well, yes, R of t equals P0 plus TD, but what is that? Yeah, that is a line, a half line, or a ray. So a half line starting from a fixed starting point, having one end without the other one, so traveling at infinity. What is a line with a fixed starting point? How many points are on this line? How many individual points are there? An infinite amount of points is on this line. What do those points have in common? Well, that is just turning the question upside down. What do those points have in common? Pass the mic over. Yeah, yeah. You're aiming in the right direction. A half line or a ray is an infinite amount of points. Well, the 3D space is also an infinite amount of points, but the points on the ray are special because they all have in common that they live on the ray. What is a sphere? And use the same argument. How many points are on this sphere? That is again, a sphere is again an infinite amount of points, or an infinite amount of points form the sphere, and that are all those points that live on the sphere, and all those points have the same distance to the sphere's center, and they all have in common that they are living on the sphere. We're aiming at set theory. So again, what is a ray in terms of set theory? In terms of the infinitely many points that are living on the ray, or sitting on the ray, or whatever you want to call it. Do it a bit more formally. A ray is a set, call it R, fancily written, of all points R of t on the ray. Okay, a bunch of points. What do we know of those points? We can write a formula for this set. You've seen it already. We've used it as a definition of the ray that was containing the line equation with this restriction. Yeah. Yeah, pretty much. So the ray R is the set of all points, again the curly braces, now with a different meaning, that is the opening and closing of the set. The set of points, let's call them R of t, and then this pipe, that means the set of points for which R of t is equal to P0 plus Td with t greater or equal to 0. And it doesn't matter if the absolute value of d is 1 for the sake of this argument. So we have a set of points. Okay? What is the sphere? You said it already. The sphere is the set, let's call it S, of all points x on the sphere centered at C with radius r. And you can write this down. The set S equals, curly braces, all the points x for which the distance from x to C is r. Okay? Now you have two sets. Do you know how to find the intersection of two sets? Because we need to find intersection points of the ray and the sphere. So yeah, we need to find the intersection of ray and sphere. How do you write that down using the operations that you know from set theory? Is there an operator? Yeah, of course. Yeah. We're still at set theory at this point. There will be a linear equation that follows from this, but this is the equation, or this equation you can actually look up in a formula book. We just do the intersection. We want to find the intersection of the ray and the sphere. If we say the ray is a set of points, the sphere is a set of points, then set theory provides an operator, and that is just the intersection operator. And that is, and what is the intersection? What does the intersection mean? Which points do I get if I have two sets and I want to find the intersections? What do those points have in common? Yep, pass the mic. The intersection of two sets is again a set of points, and that is the set of points that are in both sets simultaneously. That is the intersection. And in this example, that is the set, let's call it uppercase X, that contains the points x0 and x1. So this one and that one. And there is a formula for this. There's the good thing. And it's not that difficult. Maybe, yeah, how late is it? Anyway, probably have time for this. Yeah, I think we should get that. All right. Questions up to here? Yeah. Why do we have an infinite amount of points? We have exactly two. Why do you think that is an infinite amount of points? And maybe that is a bit nitpicky at the moment. We're talking about a sphere. We're not talking about a ball. There's a difference. Yeah, that is, we just have the sphere, so the surface, is it the surface of the ball or the surface that contains the ball? Anyway, it's just the surface, so we have 2 points, this one and that one. And I would say we could have also the case where we have 2 points that are identical, but they are still 2 points, important. And we could have a configuration where we still have 2 points, but they are not real. They need complex numbers or imaginary. They are imaginary. And then we're just missing the sphere. So we have 2 points. We do the math later, take the blackboard for this. Let me maybe just finish this, because that there's not much to follow in the slides, and then we can maybe make a little break and do the math on the blackboard. It's not that complicated, no worries. Any more questions? All right. So, if we have the intersection, we just need to compute the intersection, or the color at the intersection. The color at the closest intersection, that is important, because otherwise, I want to take the color at the closest intersection. That is the point we're seeing, not this one. we need to compute the color at the closest intersection. For this purpose, we can use local illumination. That is the topic of next week, 2 weeks. Next week is a holiday. That would give us just opaque surfaces. We could use reflection. No, not opaque. Opaque non-reflective surfaces. We could use reflection. We can reflect the ray, seeing different stuff. We can use transmission and or reflection, refraction, going through the object. But if there's no intersection, we just need to determine any background color, and this could just be the color that we have set as a constant for the scene. And this can really be any color. All right. Anything else to add here? Any questions? All right. Then I really think it is a good idea to maybe make a 10-minute break. I'll put a static slide in the video so that I can switch off the camera, and we'll be back at 3:45. So it's 10 to 11 minutes. Okay? Good. Take a break, get a bit of air, drink something, and then we do pretty simple math on the blackboard. No worries. Right, see ya. Back again. All right. We're already 1 minute late, but anyway, let me pick the first slide that needed some math support. This one. That should be, where is it? That one. We need to compute the gaze direction, the up direction, and the side direction. All right, how can we do that? Let me take the blackboard, this one, and there. That should do it. Our camera is looking this way. Well, it's too long. That is the gaze direction, and this is pretty easy to compute. Why might this be easy to compute? Let's call this P0 because that is the starting point of the ray, that is the position of the eye, that is the origin of the ray, the point of view, however you want to call this. How could we call the point that we are looking at? And where is it in this picture? Well, yeah, apparently the point that we are looking at is somewhere in the direction that we are looking in, so in the gaze direction. Let's say it's here, and call this center of interest. And that is a pretty simple way to aim the camera, to just say, I am standing here, and I am looking at this very point. Because then I have two positions in 3D space and can compute their difference to get something along the line of g, normalize it to get g with a length of 1. But this setting, I'm standing here with a point of view sitting here, looking at this point, is much simpler to determine than to say, okay, this is my point of view and I'm looking somewhat in this direction to enter G manually. It's much simpler to say, okay, what is the position of a teapot? Well, take 3 numbers, there's a position in 3D space, and then take the difference between the center of interest and the position. Okay, so where can I do this? Let's say G dash is C minus P0. Okay. How do we compute G? Well, we take G dash and divide it by its length. If G dash, the vector starting here going all the way to C, let's say it has square root of 17 units of length. If I divide the square root of 17 units of length by the square root of 17, surprise, I get 1 unit of length. How do we compute the absolute value, or the length of a vector? Let's take a vector let's just add a vector arrow for this very line, and all the other stuff is vectors, so don't make me write all those arrows. So this is the vector, and that are scalars. How do we get to the length of x? Yes, that's just the square root of x squared plus y to the power of 2 and z to the power of 2. That is closely related, if not the same, to the Pythagorean theorem. Just basically just the same. There is another, let me think about, is there another fancy way of writing this? No, not at the moment. All right, so that is G. Okay. Now we need a vector that is, that is unfortunate, orthogonal to G, that is pointing to the side. So we need the vector that is pointing straight out of the blackboard, and that is the vector S. How do we compute this vector that is pointing this way? We need another vector to help us, and that is going to be the up-ish vector. And let us take this one as u dash. That is not the final up vector. That is just a vector that is closely related to the up vector. Let me take my phone and aim it at the teapot. And if you're looking from the side, I need to tilt it a little. So the up vector gets also tilted. But for the sake of simplicity, it's not that wrong if I say this is up, just for the moment, because the up vector is pointing more to the ceiling than it is pointing to the floor or to your side. So that is why I said up-ish. All right? If I would need to turn the camera upside down, this would be up. Whoops! That is why they always break. Anyway, and this would be the up vector if I flip it. But I'm pointing the camera in this direction, and then we have the up vector here, the correct up vector. But I say, for the moment, let's imagine this is up. Okay? So for just a moment, let's say this is up. Why is this helpful? Because that is just the y-axis of my global coordinate system. And that is why I don't take this one, because what is this? Somewhat close to the y-axis, not quite. There is some x direction, some z component. The y-axis will suffice. How would this help me in computing the s vector? Just a second. Yes. We need to compute the cross product of both, because the result is going to be a vector that is orthogonal to both of the input vectors, if you will. This is always to pay well for any chiropractor, because you need your right hand and do crazy stuff with it. It's a right-handed rule. You take the first vector, that is your thumb, point it along the first vector. Take your second finger and point it approximately in the direction of the second vector. Let's say they need to be in the same plane, and now it's hurting a little, but anyway, the third finger then is going to be orthogonal to the others, and that is the cross product in a right-handed coordinate system. First vector times the second vector equals the third. Okay, so side is gaze cross up. Well, not quite. Where is a sponge? Well, there it is. Not quite. The side vector is gaze cross up, up-ish, divided by the length of this vector, because we need a unit vector once again. How to compute the correct up vector? And this is that one. Well, that is cross product again. Let's see how to do this. One. That is bad. U vector, S and G. Yeah, S and G, and that could be up. Otherwise, you could say, okay, there is not the gaze direction, but we have a back direction, the side vector, and the up vector. So be creative. But again, you need a cross product of two vectors, and you get an orthogonal vector, a vector orthogonal to both of them. So somehow gaze and side, and it was side and gaze, and then you get up. So up is side cross gaze over the absolute value of side cross gaze. Okay? And if you want to compute cross products from 3D vectors, just look those up in a formula book or in a textbook. That is pretty straightforward in 3D. That is fortunately something where you need to draw crosses on the numbers, and you get the result. Okay, that is the view coordinate system. You can compute the gaze vector, the gaze dash vector, from the center of interest and the point of view. So this one, that is the point of view. You normalize it, then you get the gaze direction. Then you compute the side vector with a vector that is pointing approximately upwards, and do this as simple as it can be. Do you take a landscape picture, that is a y-axis? Do you take a portrait picture, then it's either right or left, depending on your camera. So x-axis or z-axis, if you will. And that is much simpler than computing the correct direction, because that yields the side vector, and from the side vector and the gaze vector you can compute the correct up vector. Okay? Nothing really much to it. Any questions for this? No. Okay. Then let me go to a different slide, and that was this one. We need to do ray sphere intersection. All right? So we have the ray as a set of all points R of t, for which R of t equals P0, plus td with t greater than 0. And again, this is a vector, this is a vector, this is a vector, and this is a vector. But let's keep that in mind, which is a vector, which is a scale. Maybe I draw vector arrows. Anyway, it's a bit clearer. And then we have the sphere as all points on the sphere that are located at a distance from the sphere's center that equals the radius of the sphere. That's a good decision to write R with a vector arrow. How do we denote this in maths? How can I write down the condition for those points? I'm looking at the vector from the point to the from the center to the point on the sphere, and the length of this vector needs to be r, the sphere's radius. Careful, this is a scalar r, and this is a vector r. Okay? We should simplify this for the moment, because the sphere that you should be using at the beginning should be a special sphere. Because we're doing transformations later, and transformations will lead something called translation, that is basically move stuff around. What can be left out if we are able to move stuff around? There is a tool to it that will be in the chapter transformation. And we can leave out one of the symbols if we are able to move things. Which one? If we say for the beginning, the sphere that we are intersecting is located at the center of the coordinate space, at the center of the world, well, that's too important, at 0, 0, and we can leave this out. If we can only do spheres located at the coordinate origin, so at 0, 0, that's pretty boring. We want to do spheres everywhere, so we need a tool to move things around. This will be translation in the chapter of transformation, so we can do the moving around later. We can reintroduce an equivalent to C later. That is simpler. There's two annoying things still on the blackboard. One is the R here and the R there, and this R again. So the clash of notation and this R. Why is this a problem, and what could be the tool for it to go away? It's again transformation. What could be another transformation tool if one of those is movement? Or moving things, locating things, placing things. scaling things. I can make things bigger and smaller by scaling them. This is a transformation tool. So, do we need spheres with arbitrary radii, or can we afford to get rid of this R to make just one special sphere? Or to make these spheres more special? Let's just do unit spheres. If I can scale them up later or make them smaller, just need one basic building block, the unit sphere. Again, scaling will be done in transformation. And since we do this later, we don't need to complicate things too much. And now I can leave the vector arrows out because we don't have the radius of the sphere. Anyway, so this brought us from the slide to a simplified set of objects, or simplified sphere, but still it's set notation. And we still want to do R intersect sphere. I should have thought about that earlier and sent you in the break off to the library, because there is a formula book that has the solution to this in it. You can look it up, and that is the good thing if you start here and not with a system of linear equations at the moment. If you start here, you have the literal translation from finding intersections to the intersection operator for sets. Okay? And if you look up the definition, then you find that this is the set of points. How do we call them? I intersections, for which I equals P0 plus TD for T larger than 0, because in the intersection, this I has to be in this set, and this is the set of points for which the point equals this part, and for which the second equation also holds. So both equations need to hold for a point to be an intersection. And depending on your point of view, you could start with this part. That is basically a system of multiple equations. Or you could say, well, I don't need to remember this thing because I can look it up anytime if I'm just able to find the definition of this operator. That depends on how you want to look at it. So this one takes us to I is equal to P0 plus TD. Well, let's leave this out for a moment, but factor it in later. And I, the absolute value of I is 1. Okay? System of equations. 2 equations. How many unknowns? Yeah, that's correct. I have an unknown I and an unknown T. But I is 3-dimensional. Doesn't this mean I have 4 unknowns? Ix, Iy, and Iz. and t and just two equations? Wouldn't that be a problem? Nah. This is vectors. And vectors is just a fancy way of writing 3 rows as one. This is one row for ix, another row for iy, another row for iz, and then the fourth row, the absolute value of I, needs to be 1. Still 4 unknowns, 4 equations. Okay? So vector math does help a bit if you don't want to write that much. Okay. What is this guy? The absolute value of I. And what is the problem with those two equations? Can't I just do, okay, this one yields the I, and then I take the other one and get the t? It's not that simple, because those are different types of equations. This one could yield a t or an I, if I have one or the other. This equation does not yield the I. With this equation, you can just check if the I is valid. Okay? That is the problem if you want to tackle this, but that is not a big problem, but it makes things a little more complicated. Not much more complicated. Okay. 2 equations. So I equals P0 plus no. Let's start with this one. We can swap those. We need to take both, always and everywhere, but we can swap them. Let's first translate this to something maybe more tractable. What is this? Does this help? Well, hopefully. Let's see where this is going. I did not prepare this because I thought I can do it on the blackboard. Let's see where this is going, and you are invited to make fun of this. Where would you want to start? Well, one strategy would be take this equation as I, put it in here, reorder it to get the t, and put the t in the above. Okay? But what to do with this one? How can I write this in a maybe better way? So you say, you were suggesting this is the square root of I squared. Then I would say this is just I. Careful. Does not work that way. And what is the square of a vector? I was just too lazy to write this vector error, but that is a vector. But again, vector notation to the rescue, maybe. There is a square root, and we already figured that this is ix squared plus iy squared plus iz squared, and I was hesitant. So when did we do this? This is basically just this line. I was hesitating to show you a maybe better notation for this. Does this look familiar in any way? And this will bring us back to I squared, because you could think of this as I squared. Maybe not as I squared, but anyway, if I were a number, what would be I squared? And then you're on the right track. What is a different way to write I squared if you only had multiplications? Yes. Is this I times I? Or is this the dot product I times I? The dot product of I and I. What is the dot product anyway? Okay, one aside. We have I, and that is Ix, Iy, Iz, and since I'm out of space, this is a column vector written as a row vector transposed. What is I times I? Well, since this looks like a multiplication of scalars, let's say take I as a row vector and multiply it with I as a column vector, and forget about vector math and do matrix and multiplications instead. It's just the same, just a different notation. You could do I times I, if you will, and if you're more the electrical engineering guy, it is this notation, means all the same. Let's take this one, then it's obvious that I needs to be a vector because it's transpose of a vector. Row vector times column vector, that is a scalar product. And then, this looks quite familiar to I squared, what you suggested in the first place. And then if we say this is 1, do I need the square root? Do I really need the square root? Do I really need to write I is 1? This is positive anyway. This can't be negative. Better not be. Does it help? No, that was nonsense. But anyway, I could square both sides, since this equation is only to check the other ones. Okay? So, I transpose times I needs to be 1. Okay, why did I start here? No idea. Anyway, we could even do it here. This is I transposed times I. Okay, good. Yeah, then why not do it? We take P0 plus TD transposed times P0 plus TD untransposed equals 1. That is this equation. I flipped both, and we have then in the end I equals P0 plus TD. We need the second equation. Okay? probably the math people are going to kill me for this notation, but it works quite well in terms of computer graphics. Anyway, does that look familiar from common numbers? Not from vectors. Forget for a moment that this is vectors. Forget for a moment that there is a t. Then again, this is just, again, something squared. And this is a sum squared. Where did you see a sum squared? How to compute a sum squared? Well, maybe you look at school math. I hope you learned about this guy. What is this? This in the video. So this is the first binomial equation. Maybe this is called in English. So a plus b squared as a total is a squared plus 2ab plus b squared. Well, again, the math people might want to kill me for this, but vector notation is sort of a fancy way of writing stuff. So this should be p0 squared, right? If we start writing this out. P0 squared is a bit difficult to write or to do, so we learned that we need to write it that way. P0 squared. Okay. Plus 2 td, that does work, plus, now we need to square a vector, but we can square t, and then again, dt d. Okay, and what was that? 1. Does that work? That is a scalar product, just a plain old number. 2 times t is a plain old number, times d, that is a problem. I forgot the p. I forgot the p. P0, it is a times b. So this is the a times b, fancy writing with the vector stuff and so on. Scalar product, plain old number, times t, still a plain old number, times 2, a plain old number. This again, t squared, plain old number. Vector d transpose times d is a number. A number could be 1. Okay, matching data types. Good. And I equals p0 plus t d. Then again, how do you solve this one for t? Because you need to solve this one for t in order to put t in here to get the I. That is a quadratic equation. You can move this guy over here. Do you need to move this guy over there? No. No. No, don't let me go that far. Leave it here. That is a quadratic equation. The important thing, this t, this guy here, and that guy there, is the x that you used in school for those kinds of equations. Now the x is just called t, but the mechanics is the same. You can use, that should boil down to some sort of PQ formula. You can solve for t, put the t in here, and get an I. Careful, this yields 2 t's. So you get 2 t's over here. And you need to think about which x, or which I is the closer one. And this can easily be determined because the PQ formula should contain something along the line of t equals something. So, no, let me do it this way. Some blah plus or minus some other thing, and maybe this one. Maybe this is the ABC formula, or this is a PQ formula. Anyway, that is the basic shape of this thing. And then something is here, you have the square root, you have another thing down here, and you have a plus or a minus. And you then carefully look at this, and depending on if you take the plus root or the minus root, you can see if the one is bigger than the other. And then you find a t0 and a t1, and with a bit of care you can say, or you can make it in a way that t0 is the smaller one, t1 is the bigger one. And if t0 is positive, that is your smallest intersection, or that is a t for the smallest intersection. If your t is negative, there, you need to make sure that the t1 is positive, and then that is the closest intersection. And if the t1 is also negative, there is no intersection, careful, in front of you. And that is bringing back this guy. It could be that you're taking the square root of 0. Then I would say you still got 2 t's, but they happen to be the same. And then you pick any of those to get the closest intersection, but there are still 2 t's. If you're taking the square root of negative value, you don't have real valued solutions to this quadratic equation. And this just boils down to saying the ray misses the sphere. So, if you notice that you're taking the square root of a negative value, you're done. You're missing the sphere. If you're taking the square root of 0, it doesn't matter because you still can take t0 as the closest intersection. If it's positive, you're done. If it's negative, you're also done, but you're not seeing the sphere. If you find t0 to be positive, you hit the sphere and you have your closest intersection. If t0 is negative and you have made sure that your t1 is greater than your t0, then you need to check the t1. Just as a note, it could be that carefully looking at this equation turns out that you need to do it this way. That t0 requires the minus to get the closer thing, and t1 requires the plus to get the thing that is further away. And that is what I meant. Look carefully at this equation to set this up properly, to make t0 the closer t, and t1, no, not the closer t, the smaller t. And smaller could also mean negative, with the other one being positive. So smaller in terms of the number. And then you get to the intersection that you want to see. All right. Again, school math. A bit hand-wavy with this vector notation and the binomial equation, but it just works in terms of finding the intersection, luckily. All right. Any questions? I thought so. Someone would be raising their hands. Yeah. All right. Terrible noise. Okay, so why could I say if I have I, now I'm going to draw the vector arrow, if that is 1, then this is pretty much the same as saying ix squared plus iy squared plus iz squared. Square root of this equals 1. That should be the same as saying I could square both sides of the equation. It's just squaring both sides of the equation. Am I missing stuff there? Probably not, because the result of the that's it. That's what I was missing before. You can use squaring both sides of the equation to have the same thing. That is not the same, it's an equivalent transformation. It's just reordering or finding one of the things in there. If I square this one, I need to square this one. Squaring 1 is easy. That is still 1. And this leaves me with ix squared plus iy squared plus iz squared. I only need to be careful when the left-hand side of the equation can be negative. When there can be cases, there could be cases where I have an equation where this side can be negative. If I then square it, I lose half of the values because I'm just mapping the negative ones to the positive ones by squaring them. But since this is a square root and the result of a square root is always positive, I'm safe here. And then this again requires you just noticing that this is a scalar product where you say this is again now the same, that is not an equivalent how do you call this in English? Transformation of the equation. This is just ix times ix plus iy times iy plus iz times iz equals 1. And if I say this, and that are the components of the first vector, and this guy, and that guy are the components of the second vector, then I can write this down as, again, this is the same, first vector transposed times second vector untransposed equals 1. And then, coming back to this thing, that pretty much looks like the square of I. I can't square vectors, but since I need to put this equation in any way, that is the I equals P0 plus TD, I put it in here, I put it in here. This still looks like something squared. This something happens to be a sum. That brings me back to here. Then I'm getting something squared. This something is a vector, so I need to be a bit careful with the notation. The vector squared is a scalar product, so this is vector t times vector. But I can think this way and still be using vectors. All right. Questions? Ha! Finally got them. All right. Good. So, and we're back here. Anything more to add? Well, if you want to really want to implement the ray tracer, you can read this explained slightly differently in this black book, An Introduction to Ray Tracing. That is, I think that was the Eric Haynes book. I think I mentioned it in the intro slides. Is it Eric Haynes? No, Andrew Glasner. That should be Andrew Glasner. That is this black ray tracing book from like the 80s, 90s, something like this. It is freely available online. It should be available via the real-time rendering website, the website accompanying the book Real-Time Rendering. There are links to several ebooks, and this should basically explain all this stuff from maybe a different perspective, but there you should also find the equations. Otherwise, they are recorded anyway, and you can look them up anytime you want. Anything else? Good. Then that was the official ray tracing part. We will stay in the Zoom meeting and here in the room for discussing the projects, at least briefly. And next week is a holiday in Germany, so we see each other again on the 8th of May. Good. Final chance? Anything to add? Good. A very brief introduction to ray tracing with some maybe twisting math the way that we need it to work, at least notation-wise. Anyway, computer graphics in the summer term 2025 at the Bocholt campus of Westphalian University of Applied Sciences. See you in 2 weeks. Thanks for watching.